All right. So chapter 11 and 12 basically are the crux of statistics. It's basically the end result of when we're looking at it, like, okay, we've got this, we're going to do a study to test it, we've got the data. Now, how do I determine if what I thought was true is true or not true based on my data? Everything that we're going to look at going, or basically even in chapter 10 and going forward, means that we have good data. Okay. If you've collected crappy data, you will still be able to go through and do all this work. You get crappy results. Okay. So the better the data that you have going into the studies and into the actual testing part of it, the better the results you're going to get out of it and the more valid those results will be. It doesn't mean you can't do it. People do statistics all the time with crappy data. Okay. It happens. It's just you have to be aware of that situation when you're looking at the actual results of it. All right. So if you've ever taken a science class, which if you graduated high school, you've taken at least one, you've done hypothesis. You know what a hypothesis is. So when you did the whole scientific or the scientific, whatever the scientific, what's it called? Method. That's it. I'm like, there's another word after that. Method. The first thing is make your hypothesis, then you have to test it and do all this other stuff. So same concept in statistics. You come up with your hypothesis. That is your statement or claim about a characteristic of one or more properties. Oh yeah, I printed out the tables for you if you want to come grab one. That is the most important piece. That is what you're trying to test and claim. Okay. Then the hypothesis test, which we're going to look at today, is a procedure based on the samples that you collected to make a claim about that hypothesis. That either the hypothesis is true and we're going to accept it, or the hypothesis is false and we're going to reject it. Okay? We have two hypotheses that we're always going to have when we're looking at these studies. They relate to each other. They're both based on the same concept. The null hypothesis, which is denoted as H naught, which is the H with a little zero next to it, is a statement assuming that the information will be, basically, it's that whatever you're testing is equal to what is there. So it's the value of the population parameter, which could be anything, what we're looking at. The statement is assumed to be true unless we find sample evidence that indicates it is not. The alternate hypothesis, which is denoted as H with a little a underneath it for alternate, is also a statement about the value of the population, but this is a statement where we're trying to claim evidence to support. So our alternate hypothesis is basically what we're testing for. The null hypothesis is stating that basically the status quo is true, is the best way to look at it. It'll make a lot more sense when we start doing some problems. It sounds weird, but so here it's a very simple case. The null hypothesis is the defendant is not guilty. Because in the United States, you're assumed to be innocent until proven guilty. Okay? Lots of arguments for or against, like if that's actually true or not, but you are assumed to be innocent until proven guilty. So your null hypothesis is you're not guilty. The defendant is not guilty. Okay, because that is the status quo. That is the standard action. The alternate hypothesis in this case would be the defendant is guilty. That's what they're trying to prove. Okay. All right, let's look at this one. Every single problem we're doing tonight, the very first thing we're doing is those two things. So by the end of the class, you will understand perfectly how to find those two things. Okay, because that's the very first thing you have to do for every single problem. All right, so a molecular biologist has been investigating several species of wild potato plants. She believes she's discovered genetic properties that will increase the yield of the standard species. She has genetically engineered these new properties into a standard variety and produced a new variety. The standard species yields an average of 2.34 pounds per plant. That's okay. There's tables. Thank you. She wants to know if her new plant has a superior yield. So, what is she trying to test? What's she trying to find out? Correct. Okay, so that's what she's trying to test. She's trying to show that her new species will produce more than the original species. Okay, perfect. So, in this problem, what information did they give you? Which population parameter did they give you? Did they give you the mean? Did they give you a proportion? Or did they give you a variance? They gave you the mean. Okay. We're only going to be looking at two possible situations today. We're only going to be looking at if they give you the mean or a proportion. Okay. We're not going to look at the variance. I decided I'm not giving you another set of tables and numbers to deal with in 2 weeks. Okay. So we're only doing those two things, mean or parameter. So in this case, it's the mean. So my null hypothesis. So my mean equals 2.34. That's my null hypothesis because that's the status quo. My alternate hypothesis is what she's testing, and she wants to know if her plant has superior yield. So she wants the mean to be greater than 2.34. Okay. So the null hypothesis, 99.9% of the time, is always equal. Okay. It's always going to be the mean equals or the proportion equals that value. Your alternate hypothesis is going to be your not equal to, your greater than or equal to, your less than or equal to, your greater than or less than, those things. Okay. That's going to be what you're trying to test. Because in essence, you're always trying to test that something is different than the norm. Because otherwise, why test it? If it's the normal, I don't need to worry about it. That's what it is. So we're always trying to test if something's different than that. So null hypothesis, the norm, alternate hypothesis, what we're testing. Does that kind of make sense? Makes a little more sense than the initial definition that was on the board. Okay. All right. Okay. Take this one, come up with your null hypothesis and your alternate hypothesis for this one. All right, what's my null hypothesis? Mean equals 10. What's my null hypothesis? Less than? Okay, so it says if there's a problem with it, right? So that could be either direction, right? Which is exactly what you said. So I can't say less than or greater than, because that would be a mess to be able to try to test. What we say is it's not equal to the mean. Basically means it's something different than what it's supposed to be. Okay. So this one is known as a two-tailed test. Remember I talked about last class, we were talking about one tail and two tails? This is a two-tailed test because it's on either end. Right, it's on either end. The one that we just did a minute ago, the first one we did, this one is a one-tailed test. Okay, because we're only going to be looking at one direction. We're either going to be looking at a greater than, so on the right-hand side of the chart, or less than on the left-hand side of the chart, because I was going to say it backwards facing you guys. All right, so you have to look at that chart and determine which direction you're going. Okay, so we can have a one-tailed test or a two-tailed test. All right, the only time you're going to have a two-tailed test is when it's not equal to. And the one-tailed test, the direction of the arrow is going to tell you which way you're looking. You're either looking at the left side or the right side of the graph, depending on if it's greater than or less.
So you'll never have like less than or equal to, they'll be going the other.
You could have less than or equal to, rarely. And in that situation, when we look at the rejection, if it falls right on that one line, you're going to see why it matters. But that's extremely rare that you're going to have less than or equal to it. Because, again, you're trying to test if something's changed. So if it's equal to it, it's not necessarily changed. So, again, those are situations that, can they come up? Anything can possibly come up. Are we going to look at one here? No. Okay. All right. Oh, no, you're fine. You weren't the only one that was close to being like at 8 or 5:30, like there was like a third of the people here. I was trying to figure out what was wrong. Yeah. All right. Come up with my null hypothesis and alternate hypothesis for this one. You're right. There's no numbers in this one. But reading the problem, you should be able to come up with what they're talking about.
Null hypothesis is going to be that there's not overwhelming evidence or there is.
The null hypothesis is always the status quo.
That makes sense.
Doesn't have sufficient support, and then she's also computer sheet.
All right. So what last class, actually, we'll take one step back. What are we looking at in this situation? Are we looking at a mean or are we looking at a proportion? We're looking at a proportion. Okay, so this is going to be a P, not a mean. Okay, so that's step one, figure out those two pieces. Okay, and we're going to look at both those cases tonight and how to actually test them. All right, so now, last class, when we were talking about it, what was the default view for a proportion if we did not get something? 50-50. So the null hypothesis is exactly 0.5. Remember, the null hypothesis is always equal. Okay, so we're going to make the assumption that it is a 50-50 split. Okay. The alternate hypothesis, she wants to have significant support, which means greater than 50, but greater than 0.5. That's my alternate hypothesis. Technically, if you want to look at it, yes, but in this case, we can't say, you're never going to say less than. The null hypothesis is always going to be equal. Okay. We don't, because you're going to see once we start doing the test why that other part doesn't matter anyway.
Would this be considered a one-scale test?
This would be a one-tail test, correct, because we're only going one direction.
So for one, kind of going from that 0.5 and then forward.
Yeah, so anything over 0.5 would work. Would be considered significant support for her. Again, this is only step one of like 6 steps that we're doing in the actually testing. Okay, so. All right. So when we're creating the hypothesis tests, 2 things that we always need to find first. First thing you have to determine is, what are we looking at? Are we looking at the mean, the proportion, or in future classes, if you're taking step 2 and stuff, variance? Then you're going to determine the appropriate value to use in the null hypothesis. Okay. So sometimes they're going to be given to you, like the first couple of problems. The other one, the last one we did, it wasn't. But you could infer what that data was based on the information they gave. Then the next one you're going to do, the third part, you're going to decide what the alternative is, so the alternate hypothesis, and decide if it's going to be one-sided or one-tailed or two-tailed. And for those of you who like flowcharts, here's a nice little flowchart for you. Determine the null and alternate hypothesis. That's what we just did. The next thing we're going to do is we have to specify a significance level. Now, when we did the confidence intervals last class for chapter 10, we looked at 80%, 90%, 95, or 99. Okay? Your significance levels are actually going to be listed as the opposite of those. Your significant levels are going to be listed as, so 80% would be 0.2, 90%, 0.1, 95, 0.05, and 99.01. So it's listed as basically the complete opposite of what the confidence interval is listed as. The next step is we need to identify an appropriate test statistic. Now, this is going to be that Z or the t-test. That's the test statistic, the Z or the T. That's why I gave you those tables, because we're going to be using them a lot tonight. And then we have to find the value of that. You're going to have 2 values. Okay? You're going to have the value for basically the null hypothesis, and then you're going to have the value for the information you have found, the actual sample value. And that's what we're going to compare those to actually determine if it is we're going to reject or accept. All right, I got this down. Okay. Keep writing, you're fine. Again, I'm giving you the massive thing, and then we're going to actually go through and do it. Do not write that. We're only going to use the critical value method. Once we've found our statistics, we're going to find the critical values. This is where I gave you those little sticky notes and making the bell curves, because this is where that's going to really come in handy. When you're drawing them out, you can mark where your rejection region is and where your failure to rejection region is. So this way you can easily look at it and go, oh, okay, I'm rejecting or I'm not rejecting. Depending on where your test statistic falls into, you're either going to reject the null hypothesis, okay, if the test statistic is in the reaction or the rejection region, or you're going to fail to reject the null hypothesis if the test statistic is not in the rejection region. Okay. What are two things you notice about what I just said at the very end? There's two very important pieces that I need you to get. So the first one is I'm rejecting the null hypothesis, or I'm failing to reject the null hypothesis. What am I not doing? Right. I'm never accepting the null hypothesis. Okay, failure to reject does not mean accept. Okay, that's one piece. Second part is, what hypothesis am I rejecting or failing to reject? The null hypothesis. Which is the hypothesis we're trying to test? The alternate hypothesis, right? So we're not stating I'm failing to reject the alternate hypothesis. I'm rejecting the null hypothesis, or I'm failing to reject the null hypothesis. So if I'm rejecting that, which is the status quo, then we're saying that it is a possibility that the alternate hypothesis, as I said, would be true. Okay, so it is opposite of the way that you would think about it. So when I'm rejecting the null hypothesis, I'm stating that there is a chance, based on the data that I have, that my alternate hypothesis is true. Because I'm basically rejecting the status quo. And the last thing is, you want to state your answer in terms of what they gave you in the original problem. Don't say I reject the null hypothesis, state I am rejecting this based on this data. Like, it has to have meaning with the problem. All right. Ready to do some testing now? Do we have all the stuff down that's on the board? At least a general flow chart of an idea of what you got. Because in essence, this is all we're doing the rest of the night. Is we're going to do these 6 steps over and over again in different problems to see how it actually works. Oh, I can go back. That's fine.
So is it better to have this whole flow chart down over the formulating of the testing problems? Or do we have both?
What?
The what's the box that talks about how to formulate the testing problem?
It's the same thing. It's just the beginning parts. This is just literally the beginning piece. If you looked at it, those are the first 3 steps, or actually the first step. So, okay. All right. Let's go through and do it. It's a lot. I totally understand that. Okay. It totally is a bunch. And it's okay. We'll get there. This is why we're going to spend the whole night basically doing the same thing over and over again. Okay. All right. So step one. We go back and look. Determine the null and alternate hypothesis. That's step one. Find me my null and alternate hypotheses for this problem. What do you mean? Oh, don't worry about that part yet. That's the significance level, which I'll talk about in a second.
So it's gonna be mean.
Yes, this is mean because it's the average. So my null hypothesis is the mean equals something, and my alternate hypothesis is the mean and then something. So what's the status quo? 150, because that's the national average. And they want to determine if they're reading at a level different from the national average. So that is not equal to. Doesn't ask if they're reading higher than the national average or lower than the national average. They want to know if they're reading differently than the national average. So that is not equal to. So this is a two-tailed test. Very good. All right. So remember, this is the nice little chart for the different types of tests. If your null hypothesis is equal, notice that it doesn't matter. They're all equal to. The alternate hypothesis you're not equal to, you're greater than or you're less than. That's your two-tailed, right-tailed, and left-tailed. And those are your two one-tailed tests. The right side, left side. Or the two-tailed, which is the not equal to. All right. The next piece we want, we're going back to our chart here, is my significance level. So in this case, they say the level of the test is to be set at 0.05. Okay. So my significance level is 0.05. There is a reason, and I will show you in a minute, why they don't say 95%. Okay. And it has a lot to do with the tails. Okay. When we were saying 95% for the confidence interval, we were looking at the middle 95%, correct? If I'm saying, so I don't know if I actually put that in here, but we can draw this because I'll explain this because it's actually. All right. So for a two-tailed test, we're looking at this side and that side, correct? This would be 95%. Okay. So this is two-tailed. If I'm looking at a one-tailed, that's over here. All that's 95%, which means this is now 5% over here, where this over here is 2.5% and 2.5%. So when you look at your chart, when we're looking at, so this one, we would look at the 95% confidence level. This one, we'd look at 90% confidence level. Because that's what relates to that, because that's what would give you the 5% on that side. Because remember, it is symmetrical. So if there's 5% on that side, there's 5% on this side. So to come up with that number, we'd be looking at a different value. So that's why they're not giving you it as a percentage, because if you look at the chart, the percent's going to relate to the middle, where we don't necessarily know if we want the middle. Right, we're looking for the percentage. So this way it's giving me the percentage, which means I can move that around depending on what I'm looking at. Am I looking at the middle? Am I looking at a tail? Okay, so that's why they don't tell you 95% or 80% and those type of things. All right, so we've got that. All right, the next, once we've got our significance level, the next level, to validate the assumptions of the hypothesis test, identify appropriate test statistic and compute its value. So in this problem, my test statistic is going to be what? So this is where we're going back to, it's either the Z or the T. Okay? What's the difference between those two? Right, if I have the population standard deviation or the sample standard deviation. In this case, do I have the population standard deviation or the sample standard deviation? I have the population because I have the national average, right? Standard deviation. So I have the population standard deviation. So I have that. So that means I can use Z. Okay, so Z is going to be my test statistic. Okay? All right. So this is the formula for it. So you need to know your mean or your sample mean, which is 154 in this case. We need our alternate or our null hypothesis, which was 150. We need my standard deviation, which was 15. Sample size, which I think was 100. 100 is 100. So it should look like that when you type it in. In this case, my Z comes out to be 2.67. And remember, your Z table goes to 2 decimal places. So always round your Z to 2 decimal places. Can everybody see their tables, or do you want me to have them in the lights? Huh? Okay. Better?
Yes.
Okay. Too much light, I get headaches. Yes.
I don't know if I put, and then something would come, really, but I did not get that.
This is why the calculators don't have to talk, but you can't see them. All right, so you got that. Put that. Like 2 decimal. It's like it's not doing screw for the bottom wrong parentheses. Oh, okay. I just didn't hit equal. That's right. That's the problem. You missed a parenthesis again. I'm like, and I didn't hit equals after I fixed it, and I'm like, why didn't it change? I thought. This is why I really, really like Desmos, because when you type it in, it has to look the same. I just got an email from somebody who's taking my class in the fall, and like, what kind of calculator do you need? You don't need one. You'll use Desmos. You're fine. Don't spend money on a calculator. All right. So that is my test statistic. Okay. So we have done steps 1, 2, and 3. We've determined our hypotheses. We've found our significance level, and we've come up with our test statistic and computed its value. Yes. We haven't determined that yet. That's the next step. All right, so this case we were doing a two-tailed test, correct? And we were doing a 5% significance level. So when you're looking at your, I'll be nice. Hold on, I'll give you a table. You know what? No, we're not going to do that. I was going to kind of be nice, but I'm not going to be nice. I'm going to make you figure it out. On purpose, though. All right. Remember, my Z table is always giving me everything to the what? All the way over to this direction, right? So it's basically going from here all the way to that line, correct? That's what the Z table is going to give me. Okay. So which number am I looking for on the Z table? I'm looking for a 0.975 because that's 95 and that's 0.025. Remember? Because it's 0.025 on either side. Okay. 95% is directly in the middle. Okay. So, all right, we'll do it. I'm going to actually do this a little different way. We're looking at a 5% significance level, correct? Okay. So that means it's 0.025 on this side and 0.025 on that side, correct? That's what a 5% significance level is on a two-tailed test. Okay. So if I'm looking for this line right here, or this line right here, this line right there, I'm looking for 0.025 inside the Z table. For this line, I'm looking at 0.975 on the Z table. Okay?
Just adding it to it.
Yes. Now, my bell curve is symmetric, correct? That number and that number should be exactly the same, correct? Except the sign, right? Okay. So the easiest way to do this is always to look at your negative side.
What's 1.96 there? So that's just standard.
No,
That's for if you're doing 95%.
that's my significance level was 0.05. So this chart right now that I'm looking at is based on a 0.05 significance level.
Like,
It'd be different.
0.1.
Yes. So I've got 0.25 on one side, 0.25 on the other side, because it's a two-tailed test. Does everybody understand that? Okay. So on your Z table, and actually, I'll grab one now. Let's look at the exact Z table. On the negative side, find me 0.025. So inside here, you're not looking at the Z's, you're looking inside. You're looking in here. And you should get negative 1.96. Everybody find 0.025? If not, tell me and I'll come see you. Because this is like actually probably the most important part of this whole thing. If you can't find that number, you're never going to be able to test these afterwards. Yes, you should get negative 1.96. Since it's symmetric, that means negative 1.96 on one side, 1.96 on the other side. I don't have to go up. Now, if you looked at the other side and looked at 1.96, it's 0.975. It's the other side. You don't need to do them both. We know it's symmetric. Find the negative version. You know the positive one is exactly the same, just the positive one. Okay?
So what's the purpose of solving for Z then, if we're just?
We're not done yet.
Okay.
We haven't tested anything yet. Remember, we need something to test against. That's what my significance level comes into play. Okay, so we need to set up where our rejection range is and where our failed to reject range is. That's based on my significance level. Okay, the test statistic I now am going to place on this chart to determine if I'm going to fail it or accept it, or not fail to reject it, I should say. Hold on a second. Let's see if I can find my nice little. Nope. That's right. I'll use this one. I just needed a clean chart. All right. So we have this. Red is reject. Green is failure to reject, right? What was my test statistic when we calculated it? 2.67, which is over here, correct? That's 2.67. It's in my so I'm rejecting my null hypothesis. So you have two steps we need to calculate at the end. You need your test statistic, and we need to know the region we're testing it in. We need to know that reject region. That's based on your significance level. In this case, my significance level was 0.0 or 0.05. So that's where the negative 1.96 and 1.96 came into play. My test statistic, 2.67, is in my reject region. So that means I'm rejecting my null hypothesis. Okay? So in essence, remember what we did last time, or last class, when we were looking at the I'm really blanking tonight. Hold on. Confidence interval. We're looking at our confidence interval. And I said when it's outside of that, it's really rare, right? Well, if my number was over here, that's too rare for that to be true. Okay? So since I'm in that region, that means that it would be too rare for that to happen if the null hypothesis was true. Okay? So, do we reject the null hypothesis? In this case, yes, there's significant evidence that at the significance level, that we reject the null hypothesis in favor for the alternate hypothesis. Okay? It is going to change based on that significance level. We did this at a 0.5 or 0.05 significance level. That's where those ranges are. If we did it at a higher level, we might not have been able to reject it. Okay? So that's why that's important, that significance level that we're determining at. Since we're rejecting it, since we're rejecting the null hypothesis, okay, let's go back to my original problem. What can we say about the Lincoln High School students? No. You said one word that was wrong.
Yeah, and it's possible. You can't fully accept it.
Nope. That wasn't the wrong.
They score higher or lower.
That they're not scoring at the national level. Okay? That's what we can say. We're rejecting the null hypothesis for the alternate hypothesis. And the alternate hypothesis states they are not testing at the national level. You cannot say they're testing higher than the national level, even though based on the data that we've got here, they probably are. Because we did a two-tailed test, not a one-tailed test. Okay? If we did a one-tailed test and said, were they testing higher than the national average, they still would, it would still have been in the rejection region, and we still would have said yes. But that wasn't what this question was asking. Okay? So once you make your final statement, you have to go back to the problem of what your alternate hypothesis is and state it based on that, not what you think is nice at the end.
So if they're not scoring,
They're not scoring at the national average, or they're scoring at a level different from the national average, because those are the exact words they used in the problem. Okay? I know it's a lot of steps.
So once you make your bell curve, you're really just figuring out where.
The test statistic falls.
I know it's more, but like in theory, it's kind of just like two steps.
Yeah, you're really comparing two numbers. Yep. The biggest thing about making out the bell curve and drawing out the bell curve is to make sure you're looking at finding the right number and make sure you're doing the right test. If it's a one-tailed, two-tailed, left side, right side, those type of things. That's really the piece that's important. Because if you didn't draw out what we just did in the last one, where you have to 0.025 to 0.025, odds are you would have looked for 0.05 and got the wrong number and made that mistake. So those are the little errors that come up when you don't draw it out. That's why I said it's drawing it out makes your life so much easier, especially at this stage where you're really not insanely confident in doing it. Like once you get really good at it, yeah, you're just going to know it and you don't have to worry about it. But at this point, drawing it out is going to save you a lot of little mistakes that you can make. All right. Step one, starting over. Find me my null hypothesis and my alternate hypothesis.
Yeah, so the mean is 16,000, but we're finding,
Right for a second. All right, so let's look at it. So my null hypothesis. So what'd they give me? Yeah. So that's my mean. It's 16,000. My alternate hypothesis is increases, so greater than. Okay, so this is going to be greater than. Okay. So my significance level is 0.01. So if we look at a little nice little bell curve here, we're just going to draw a quick little bell curve. We're looking at over here, right? So that's 0.01. Correct? So which number am I looking up? So now you can do this either way. Me personally, I always use the negative side, because then I can look for that exact number right there and not have to worry about subtracting things. Okay? So I'm going to look at the negative side and I'm going to look for 0.01. Yep. Because it's symmetrical. So one of the nice things about the bell curve being symmetrical. Yeah, you want, if it's, you can't find the exact value, you find the closest one to it.
Because it's 17 over.
Right, and the other one's 10 under. Yeah. So we're going to use the 2.33. And since I'm on the positive side, I'm using positive 2.33. It'd be negative. Right.
So you're always just gonna try and find the significance level on the table, and that will give you.
Well, that's going to give me that number for the significance. That's going to give me my the z-score.
Yeah, you still.
For the
you
right.
still solve for the z-score.
Yeah, I still need to find my test
But
statistic.
in order to find that kind of range to
Yes.
determine if you reject it or you fail to reject it, you always try and find the significance level. of this.
Correct. Yep. Okay. So two things. Everybody understand where I got the 0.01 and why I put it over where I did? Okay. Everybody understand where I got the 2.33? Okay.
That on here.
so that's our test statistic.
So no, that is not my test statistic. That is significance level. So my significance level is 0.01. Right, that's the closest one to it. Because I go this way, it's 17 over, this is 10.
But so this, because it's positive because it's on the.
Correct. Yes.
Okay.
So we're finding if the test statistic is inside that range.
So we're looking in here.
Yep.
For 0.01. 0.01. So that's 0.01, right? But that's 17 over. That's close, and that's 10 under. So I use this one.
I was like,
So now, so my Z is negative 2.3. Okay, and since it's on the positive side, since I'm on that right side of the graph,
Yep.
I'm just gonna make it positive.
Okay.
It'll always work. The beauty of symmetry.
So the rejection region is 2.3 or anything higher than that?
Yes. Yeah, so my rejection region is that little squiggle that I put in there. That's the rejection region. So now I need to find my test statistic. So now I have to do that Z equation. So my mean, my sample mean is, but they didn't tell you. Hold on. That means they showed it at a later point in the actual problem on my screen. Hold on. There we go. I hate when they do an example and they don't put all the data right at the beginning. It's like, why? So we're gonna shift this up a little bit. All right. So my sample mean is 16,200. Minus the 16,000. Divided by my standard deviation was 2,500 over the square root of, and we did 1,000. All right, so that's what we got. So 2.53 is somewhere over there.
So it's inside.
So it is inside the rejection region. So we are rejecting the null hypothesis.
Is your arrow just saying that that's X or that it's inside the bell curve?
Oh, that's just X. I probably should have put the arrow the other direction.
So,
Huh?
you said it's inside the.
It's inside the
Yeah.
rejection.
That's Desmos.
How do I get it to go over the 1620 and
So here's how I typed it in. I hit the division first in Desmos. And then when I go down the bottom, I hit the division again first. Otherwise, you have to highlight and then do it. It's a pain in the butt. Oh, There we go.
That's the sample.
That's the sample mean.
That's the one that.
That was one that wasn't there. Oh, I should share back that screen. There you go.
So then the phrasing of it would be that.
So we already know what the mean is for random sample without, but we're still testing another random sample. Or is that, once we tested it, we know what the mean is? But we're assuming we tested it already.
What was your question? Sorry, ask me.
And so like, it says a random sample of 1,000 will be tested. This is suppose the random sample has to be like 60,200 hours, so we've like already tested.
Yes, that was the sample that they tested.
Yep, what we found. Yeah,
Correct. Yes. So they tested 1,000 of them. So, and then that was the mean. If that's the new mean, that means that the 16,000 is inaccurate. So that's why we're rejecting the null hypothesis. So the life of the new chips is greater than the mean of 16,000 hours. I can't say it equals 16,200. I can't say it equals anything. All I know is that it is going to be greater than 16,000. Ask it again. Sorry, I caught. So you're not. The sample mean was, I just didn't put it on there because it was the second part of the question. In the book, they asked it in like multiple parts. And, you know, the teacher and me assumes you give all the information in the original problem, and they didn't. The teacher and me would never do that. All the problems information should be there originally. All right. The only difference between Z and T is in T, we don't have the standard deviation. Okay, we have to use the sample standard deviation. All right. Everything else we did, identical. Doesn't change. Okay. Okay, so really, even the formula is almost the exact same. The only difference is it's a sample standard deviation instead of the actual signal. That's really the only difference between this. Does this give me all the data? It does. Good. Okay. All right. Step one. If I'm in my null hypothesis and my alternate hypothesis. All right, what's my null hypothesis? Mean equals 35. What's my null hypothesis?
Yeah.
Not equals 35. It says differs from. Means above or below. All right, so this is a two-tailed test. My significance level is 0.05. So I'm looking for two numbers. Which number am I going to look at in the table? Right, but which number am I looking for? 0.025. Because that's going to give me the 5 total. So you should get 1.96.
So it's 1.964 negative 1.96. It has to be
Oh.
above 1 or below this.
Hold on a second. I forgot. This is T. I forgot. This is T.
Yes.
All right. So T, we have to do one extra thing. We need our degrees of freedom. So degrees of freedom in this case, 20 employees. So my degrees of freedom is 19. So here's the nice thing about my T table. It's got all the numbers at the top. So we're looking for two tails, 0.05. And we're going to go down to 19. So it's 2.093. And then negative 2.093. We're looking at, so this is a two-tail test. So at the top, we're going to go over to two tails, 0.05. And we're going down to the degrees of freedom of 19. So it should be 2.093. I forgot we're using T-table for this one. And then we got the positive and the negative version of that. Did everybody find that or no? If you didn't, tell me and I can come help you figure it out.
So the rejection region less than that.
Right. My rejection region is going to be those two sections.
This is still 0.025.
Yes. Yeah, it still ends up being 0.025. But that number isn't actually important like to have on your table because you don't need that. That's not going to connect to anything you're going to use to calculate. Does that make sense? So the 0.025 on the Z table made it really easy for us to find the number. On the T table, it gives me that information at the top. It says one tail or two tail, so we didn't need that. And we're not comparing that number to anything. We're comparing it to the number on the bottom. Right. So we didn't have to actually worry about that piece. Correct. All right. So we're going to use our T. So my mean time to take the test was 29 minus the null hypothesis, which is 35. My standard deviation is 8 divided by the square root of 20. I swear not everyone's going to be rejected. But this is our first negative one.
Like, negative.
Which is fine. So t equals negative 3.35, which is somewhere over here. So I reject the null hypothesis. So there is significance data that at the 0.05 level, that the mean time to take the test differs from 35 minutes, or is not 35. Huh? So, yeah. So the mean time it takes the test at the significance level of 0.05 differs from 35 minutes. I want to do one more. And then I'll give you guys a break. Let's do. This one. All right, go through all your steps.
The alpha represents the significance.
Yeah, this is my significance level.
mean is actually less than 5. More.
Remember, your null hypothesis is always equal.
Oh, yeah.
So, they have the same thing, it's the- the standard deviation.
Yes. Yes.
So the alternate hypothesis is less than 5. Or
Yes.
There is no 49 though.
Right. So remember last class what I said? Anything over 30, you can just use the z at the bottom.
So it's 1.96.
It is not.
Oh, because we're only going around 2 tails.
It's one tailed.
Hopefully one day.
This is one tailed because it's just less than. So we're just looking over here. Direction.
If it was not equal to 5, we could do that, right?
Right. Not equals is two tail. Less than right tail or left. Yeah. Right tail. Left tail. Greater than right tail. Yes. Do you have the population standard deviation or the sample standard deviation? That's why it's T.
Oh, it is T.
Yes, this is T. The reason why we can use the Z number at the bottom of the T table is because it's over 30 for my degrees of freedom.
Said it's less than the price one table.
Yes,
Yeah.
yep.
What was the other?
If it's greater than, it's also one tailed. If it's not equal to, it's two tailed. So think about it, the direction you're going. Not equal to means it can go either direction. Less than means you're only going one direction. Greater than means you're only going one direction. So that's why those are one tailed. Not equal to is two tailed because it can go either direction.
Is it because it says in the beginning that they wanted to determine which would be unverified?
Yeah.
Okay, so that's how you kind of get what.
Well, no, actually, because it actually says the final question is, can the officials concluded a significance
Oh,
of
still
0.05? That's still under 5 minutes. So.
already forgot about the rejection.
So that's that bell curve.
Yeah.
That was the negative 1.165, 1645. That we got.
I forgot how to get that.
What how they got the negative one?
So,
We're not using the Z. This one using T.
Oh, then we already.
Right, but you can still use the T table to find it. It makes your life easier.
Okay, yeah.
Is the 5 in the T equation, that's the null?
That's the null hypothesis. Yeah, it's the mean minus the null hypothesis. Always.
So what is it that you look at?
So in this case, we're looking at 5. We're looking at 5 on the one-tailed at the top. The one-tailed 0.05. And then you're just going to the bottom because you can use the Z number. Because it's over 30 for my degrees of freedom.
The degrees of freedom would be 49.
Yeah. And since it's over 30, that's why I said it's over 30, you can use the Z. Would you like another one of these before we go on, before I give you?
Yeah.
All right.
What's your statement?
At the 0.05 significance level, we can determine that the move time is still under 5 minutes. Yes.
So this time it's actually not rejected. So it should always match, like the sample. It should match this, right? Like since it was 620 and not 600, and expected that the hypothesis could be right.
No.
No, okay. Because this, so the sample could be, like if the sample, if it was, like if it was below 600, if the sample average was below 600, it's still be.
We'd still be, it depends on where it falls. It depends on you're testing the test statistic. So when you can't, if there was a way to just look at the data like this without doing anything and figuring out the answer, we wouldn't do it all. Okay. So the problem is that if you were looking at this and you go, okay, well, I got a sample of 16 that was 620, obviously it's higher. Like that's what you would make the assumption on based on that. And it is higher. It absolutely is higher. It's at 1.6 above. Okay, so that's 1.6 standard deviations above the mean. It is definitely higher. It is just not significantly higher. It's not enough higher based on our significance level. So we were testing this at a 0.1 significance level, which means it needed to be higher than the 1.753 standard deviations for us to say it is definitely higher. So it could have been that within that standard deviation, because remember, standard deviation is plus and minus, right? So if 620 with a standard deviation of 50, that means one standard deviation goes from 570 to 670. Is 680, remember that's 68% of all the data, right? So it could have been anywhere in between there. So it could have been on the low end of that, still been fine. We don't know. All right. That's why we have to go through and do the testing, because that allows us to come up with a specific value that's been proven, say, okay, this is how we determine if something is way outside of the realm based on our significance level. And if it is, then we can reject. In this case, it was not as far out as it should have been. It was close. 1.6, 1.7. It's not that far off, but it's got to be higher. It had to be higher. It had to be 1.8 or something like that for me to be able to reject. And if you look at the way the calculation works, sample size has a lot to do with it. Remember, the bigger that sample size, the lower this number is going to be lower. Okay, which means it's going to make that number go higher. Okay, because it shrinks that bar. Okay, so that's the piece that really matters. They only tested 16 people or 16 engines in this case. If they had done 50 or something, maybe that would have been a lot more, and then we would have rejected. Okay, so
Why does sample standard deviation, is that something we did? before?
yeah, that's if you have the data, you would just type it into the calculator that gives you the standard deviation and the sample mean. All right, go take a break. Be back at 7:20, and then we'll do the rest. No questions. Yeah, go ahead.
So I think I'm just a little confused. So originally, when I was looking at the significance level, because it was two tail, I thought that I had to divide that because it was looking at two halves of it.
Right. So
Even
if you
though-
look, see how
Right.
the two tails 0.10?
And the, yeah,
It does it already. One tail is the 0.5. This does that for you automatically.
okay,
And that's your, if you look, your 10 is your 90%.
okay. Yeah.
So this
Because
does that
I think I was
automatically
getting
for you.
confused because when we did the
Right.
of
When we
this,
did the
'cause
Z, we
when-
had to look it up.
when we did the 0.5, this was then turned into the 0.025.
Right. Because so in essence, when we were looking at it, we were looking at the 5 on the one side, the
Right.
95%.
Okay.
So that's where that comes in.
Okay.
So it's just the thing about the tables. This
Mhm.
table does that for you up top, so you don't have to worry about
Right.
calculating it out, where the Z table doesn't.
So basically, it just kind of.
It
use
makes
the
you like,
T-
yeah.
use the
And
T.
honestly, if you look down the bottom,
Yeah.
it's all the Z's
And
that
if you
match
need,
up.
yeah.
You could easily just, so when we did the 0.25
Mhm.
for the Z, there's a 1.96.
Okay. Okay,
So
so
you
when
could
the
just
sample
use-
size is greater than 30, like when you,
Yeah.
like you said, we can literally,
Right.
we could literally find it and just go all the way down. use the
Exactly.
calculator.
Yeah.
Okay.
Yes.
Should we slightly show step of any of the
This one? Yep. No problem. Yes.
So what on here would you look up on the two table then?
No, that we found in the two table. So you're looking up on here. We were looking up, we were in the 0.1 on the two tails,
And you know that becomes.
because that's what it said.
On there, okay.
Yeah. And then it was 16 we were looking at, so we had one less. So we're looking at 15 for my degrees of freedom.
Yeah.
So I go down here to 15,
Okay,
and that's that number there.
okay, so find this on the chart.
Yeah.
And then. Where did you get how did you use this one versus this one?
For this one,
Yeah,
it was, what was it,
cause I thought it was
0.5?
this.
Yeah, it was 0.05. So we used,
Oh, so you went over there?
Yeah.
This
and then
one?
we went all the way to the bottom, I think, because the sample size was 50, right? So
Okay.
that's like, actually, sorry. Oh, this is one tail. So one tail, 0.05
Yeah,
is 1.645.
okay.
And it's negative because it's on that side. If it was this side, it would be positive.
We went over to.
So we went one tail,
Yeah.
0.05. And then since it was over 30, we just went to the bottom, use that number.
Okay. Okay, I'm sorry.
Okay.
The 2.67. The standard,
Oh, that we did, that was the Z score. That was that,
oh, that was on the.
that was the, no, that was the formula. So it was 154 minus 150. Because that was the
Standard random
mean.
variable.
Right, that was the mean was
Oh, is that the
154.
one?
This is the 2.675.
What's that? No, that was is that the national average
Yeah,
reading?
yeah.
Oh, that's the same one?
Yeah.
Okay,
So it was 154 minus 150, and then it was the standard deviation was 15. So 15 divided by the square root of 100,
and that's how you got
and that's how we
that.
got the 2.67.
But then what here, so we'd find this one on the.
So
chart?
this was the chart.
Yeah.
That was the chart.
Yep.
And this was the formula.
Yep.
And that's what we're testing. So since that's outside in the rejection area,
Mhm.
that's why we reject it.
Okay. And then, all right, and so that's how we got both. We
Yeah.
looked that up on the chart and that's how we got.
Yep.
both of them. Okay. All right, thank you.
No problem.
Wait, so how do you know whether we're using Z or T?
It's all about if they give you the population standard deviation, it's Z. If it's a sample standard deviation, it's T.
So population standard deviation?
Population standard deviation is Z. Sample standard deviation is T.
Samples.
All right. Proportions. Notice top table, exactly the same. Nothing's changed except it's a P instead of a mean. That's the only difference. Okay, you're still gonna have our null hypothesis. We're still gonna have our alternate hypothesis. It's still same thing as two-tailed, right-tailed, left-tailed. That all stays the same. Your null hypothesis is always equals. Your alternate hypothesis is the one that's going to vary. The only major change that comes when we're looking at proportions is how we find the test statistic. Proportions is always going to be Z. Never T, it'll always be the Z. And the formula for your standard deviation is what's the piece that changes. So it's the null hypothesis times 1 minus the null hypothesis divided by the sample size, the square root of all that. That's your standard deviation. You could technically just put this underneath here and just do it at one shot, depending on your calculator. It wouldn't be much different than what we just did a minute ago in the other formulas, where you have a division over division. But that's the only thing that changes in everything that we've done so far. Process is all exactly the same.
So they're always Z.
Yeah, proportions are always going to be Z because in essence, you'll know the standard deviation because you can always find the population standard deviation based on the proportion. So that's why you can always use Z for this case. Everybody good with this? All right, let's do one. Okay, step 1. I have my null hypothesis and my alternate hypothesis.
But so why is P capital there? I mean, is it? Like it's supposed to be lowercase, because that's the P we have.
P looks the same if it's capital or lowercase.
Yeah, but like because before we did capital P for probability, yeah,
Right. It's
that doesn't matter because we
Yeah.
know it's not proper.
right. I'm like, I don't know how to write a lowercase p that's like I'd have to put the line. That's uppercase. That's lowercase. Yeah, it's a little bigger. It's the problem of when you're writing on things without lines.
Yeah.
All right, so that's my null hypothesis and my alternate hypothesis. So we got that. Okay. They don't give us a significance level in this problem. So technically we can use whatever we want. The standard view, if they don't give you something, is always to use the 0.05. That's the standard one. If they don't give it to you, use 0.05. So we're using the Z table, and we're using the is 0.05. So is this one-tailed or two-tailed? This is one-tailed. So now, I'll show you another nice little trick. Pick up your T table. Yes, I know it said Z table, right? Look at the very bottom of the T table. They give you all your Z's for every value you're going to want. Okay? So, look at the top to figure out which column you're going down to look at using. We're doing one-tailed, and we want 0.05. So look at one-tailed, 0.05, and go all the way to the bottom, and that's the number you're going to use. So it's 1.645. Okay? It saves you having to look for the numbers inside here. Okay? Because it's got it all the way at the bottom on the T table. Okay? Saves you some work. Nice T table. All right, so we've got that. We know it's one-tailed. My rejection region's over here. So now we just need to find our test statistic, right? Okay. So Z equals, it's going to be I need to find my P hat in this case. So it's 352 over 520, which is what? 0.672? Okay. All right. So I have 0.673 minus 0.6 divided by the square root of 0.6 times 1 minus 0.6 divided by 520. So it equals 3.39 or 3.40. So that means it's over here. So we're rejecting the null hypothesis. Okay. Noticing patterns here? Starting to do the same thing over and over again. The only thing that really changes is how you find your test statistic. Everything else stays pretty much the same. All right. Find me this one.
Um, just, is it greater than or not equal to the 50% for the alternate?
Are in favor of building it. So I would say greater than 0.5. That'd be in favor. You need the number. Hold on. They surveyed 420 people.
I have the number in favor, but number.
No, they gave it to you as a percent. So you don't even need to do the calculation for it. They gave that to you. You needed the 420 because you need N. That's why I gave you the 420. Huh? Yes, you're still using the 0.5. Because they don't tell you what the initial thing is. So again, you automatically assume 50-50. And if you're talking about in favor, that'd be anything over 50%. So yes, P hat is 0.54. Yes. P hat's 0.54. The little chart, the table. They gave that's the results of the survey.
Yes. Yeah, so you use the Z because for its way.
You're always going to use it. for the proportion.
Proportion.
Yeah, for proportion, you're always using Z. You don't need to worry about degrees of freedom or anything like that, because you always can find you can always find the standard deviation of the population for proportion, because you have a formula for it. It's not something you're going to be given, you have a formula to calculate it. P hat is typically, you'd have to do the calculation to divide what you want over, but they gave it to you in this case with the pie chart.
Oh.
So we had the 0.5. Yes.
Thing again.
Just use your phone. There's a million parentheses this way.
I mean, you can also do it the slow way, but
That's fine.
Yeah.
You need a second set of parentheses around. Oh, first of all, you forgot the square root. Oh, you forgot the square root part. That's part of it. Then you need parentheses around that part. Decimal point there. There we go.
There's a decimal point there, the decimal point there.
There's the parentheses, the square root, a decimal point. So, in all honesty, the problem with using a calculator that doesn't show you it actually in regular type is it's really easy to do exactly that, is to miss things. And even like, I would say, oh, graphic calculator solve your problem, except for the vast majority of the graphic calculators, except for the high-end ones, also just show it in a straight line anyway. It doesn't show it in the correct math type. So even that wouldn't help you. So. All right. So this one is in the fail to reject category. We do not have, it is not significant enough to say that it is going to pass.
You go over how you got this point.
So on the Z table, I went to one-tailed, 0.01, and all the way down to the very bottom. And it gives you the Z.
And we didn't even-
Yes. Okay. So yes, this is Z. The nice thing about this T table that I gave you is at the very bottom of it, it gives you all the significant Z values. Okay. So you don't have to use the Z table to find it. If you wanted to use the Z table, you would. You'd be looking for 0.01 on the negative side, and you're going to get something very similar. I think you'll get 2.32.
And we're not.
Yeah, you get 2.33.
We're not doing the degrees of.
No, because it's Z, so that's why we can use the bottom.
I get that, but I thought we were doing the 0.5.
No. My significance level is
Oh,
0.01.
Okay.
So I go over here, 0.1 all the way to the bottom.
And you got the 0.5 from, you said.
It's,
because-
if they don't give you a proportion, the standard, the what you typically would use is 50-50.
Point five, it's just, the level.
If it's no significance, I'll use 0.05. They don't give you your significance, I'll use 0.05. Let's do this one. All right, try that one. Oh, that's why I was looking at that number.
The reason it's negative is because we're looking for less than.
Yeah, we're on the negative side of the graph. So that should have been your formula. And you get negative 1.77. So I fail to reject. It's not. How many ships do you think came into the United States last year? Take a guess.
10,000, definitely over 1,000.
For the year.
Oh, for the year, oh, definitely.
It was like a long day.
Over
500,000.
100,000.
It's actually just over 1 million.
Oh,
Yeah, that makes
wow.
sense.
Just over 1 million. Okay.
Are you talking cargo too?
Any ships.
So it could be like this small.
No, it's so when you're arriving at the US port, like if you're a little tiny like sailboat, that's not arriving at the port. These are arriving in like the major US ports. So yes, cruise ships would count, like those type of ships and stuff would count. Most of them are cargo ships actually. So most of them are like the bulk barge cargo ships. Okay. So we had over 1 million, right? They selected 50. Do you have a problem with their sample size?
Yes.
Okay.
We're gonna choose 50 out for over the 1 million.
So, but if you think about it, if there's 1 million coming in, that's like 3,000 of them a day. And if you've seen these cargo ships, they're massive with tons of like cargo containers, like shipping containers on them. Like to be able to inspect them, it'd be almost impossible to inspect them all. Or it's even impossible to inspect a significant number of them. So this is the type of stuff that happens. But in this case, we're failing to reject it because the number is not significant enough to state that the population has, or the contaminated cargoes have decreased. All right, there's my. Okay, next one. Do this one. We're gonna do this one. We'll do this one up to 0.05. They gave you your H naught and your hypothesis, so you don't have to find that part. How about they were nice to you this one?
I was gonna say, they gave us,
We're finding the details. So.
Yeah, they gave that to you. So yes. It's two-tail. Technically, it's a T table because they do not give us a standard deviation of the population. But since my sample size is 2,000, you're using the Z at the bottom anyway. Five, two tails. So you should be seeing the more of these you do, the faster you're getting at them. Because you're noticing like the things that you have to look for, the things that you need. Like you're not like, you don't necessarily have to like go every step right. Like, what you're looking for gets faster. So the more of these you do, the better you will get, the faster you will get at these. So somebody has asked in the beginning, like about the final exam, there's 15 questions on it, or they're going to have a lot of steps. Well, like this has 6 steps. Like you're doing a bunch of stuff to find the answer. That's the type of problems you're going to see on the final. The better you are, the faster you can do them. So yes, there's going to be a bunch of steps to it, but it's works its way into them. All right, so what did we get as the answer? 4.47, I think, or 6? Yeah, 4.47. So I'm rejecting, right? Because it's over here. Okay, so what is the final answer to this problem?
Following a single or the
Okay, correct. So basically, we determined that at the significance level, the weight is not exactly 25 pounds. How many of you have dogs? Okay. How big are the actual pieces in the dog food? Okay. So we did 2,000 bags. The weight of the bag was 25.01 pounds. When you go home, try to weigh out 0.01 pounds of dog food. Okay, we're talking about maybe 2 or 3 chunks of dog food.
Yeah.
Okay, so yes, it is not exactly 25 pounds. That's what we determined in it. That is my scientific statistical study. Do we care?
No.
Now, if it was 26, 27 pounds, yes, that would be a problem that we would look at. However, there is a point where when you do such a large sample size, is that you're going to reject things that, while statistically significant, has no practical meaning. Okay, so this is one of those situations where, well, yes, it's statistically significant, it doesn't mean anything in the real world. Like, there's no reason that they're going to go through and revamp all their machines to fix it because they're putting an extra 3 pieces of dog food in your dog food bag. Okay, that wouldn't be worth it. So that's one of those things that there is no set in stone way to look at it. It's one of those things that after you look at the data and you look at your information, you do make that determination. Does this actually mean anything? And in this case, no, it doesn't. This is not something that we're going to worry about in this situation. Okay. So the last section actually of chapter 11 is exactly that: practical significance versus statistical significance. Does it matter that that's something that we actually care about in this situation? That the bags do not contain 25 pounds of dog food. Because we've rejected the null hypothesis, which stated that they do actually include 25 pounds of dog food. I don't know if it's higher or lower, technically, but it's not 25. And based on the sample size, it's really close to 25. All right, I think 2 more, and then we're done. these numbers, we should just shut down the IRS tomorrow. You know, there's no point to them. Oh God, yeah, it goes to way more than 45 minutes.
They're like, we're gonna test.
Yeah.
We're gonna. There's no way it's more than 30 minutes.
Yeah.
Oh,
So
I love the data.
yeah, it's probably closer to like 2 or 3 hours now, or tomorrow. The only nice thing is actually a lot of computer systems now you literally can like they'll call you back, so you don't have to sit there and hold the phone for a couple hours. But yeah, it's ridiculous. You're just not going to get a real person anymore. Yeah.
Wow, that, right?
So this is another one of those ones. Is it statistically significant? Yes, 13 is way above where it is. Okay, so it is definitely statistically significant. Is it practically significant? Yeah, I would say based on the question where it says they must wait, they're complaining they must wait more than 45 minutes. 55 minutes is more than 45 minutes, and 45 minutes in my mind is too much to begin with.
Yes.
So yes, I'm going to say this is practically significant. So, okay. No, this is not why they're adding thousands of agents either. No. No. The problem is they can't outsource their call center to like another country like everybody else does. Because it's the US government. So so funny thing, during COVID, one of the interesting things happened is where because there's so many people at home, companies actually started contracting with people at home to become call center people. And because they were actually being able to find it cheaper here than over there. Because people were just looking at little side gigs and stuff like that. So yeah, it was a little interesting look on side bit. All right, last one.
Was that the one that wasn't failed?
This one, we rejected it. Yeah, it was way, way, way over. Sorry, I didn't mark the X there. All right, one more. You ever dread when your family member says, I have a question? Never know what's coming next. Normally with this family member, it's, I need money. All right. So what does it mean? So what are we rejecting? Is there overwhelming evidence to state that it takes does not take 45 minutes to make a cabinet? Okay.
It's over.
It's over.
So here is another one of those little statistic. Is it statistically significant? Yes, it is over. We reject the null hypothesis. It is statistically significant. Is it practically significant? 2 minutes? Have you put together a cabinet before? Have you bought stuff from IKEA?
It takes a while, but 3 days.
So the 2.24 needs 2 minutes.
I
more.
do it. I do it.
It means
Sorry.
it means
Go ahead.
the data above.
So the 2.3236 means it is outside of this. It's over here. So we reject. So it is taking different than 45 minutes. Supervisor believes it takes 45 minutes. The evidence shows that it is not taking 45 minutes. It is taking something different. We can, based on the data, we can make the assumption it's taking more than 45 minutes because of where it is, but statistically we can't say that. So the practicality part comes in is it's 2 minutes. Is that
It's-
And that's
it's 2
because we
minutes.
saw 45 and 47.
right?
And the 2.23 is not that far off.
Right. So practically, I would say it's not significant enough that it's making that big of a difference. Okay.
What is the wording that tells you that it's gonna be equal and not equal to? Because I initially
Yeah,
thought,
'cause it says
I-
contradict. It doesn't say
yeah.
like-
Right.
and-
Contradict. Differs.
So not that.
Not more.
Right.
Okay.
So a lot of times when you say it'll say greater than or increases or
So
less
it
than, like,
doesn't say less than or more than.
or something along those lines. Yeah.
It's
gonna be not equal to.
It's gonna be.
Yeah. Yep. I was right. Totally right.
It's not significant.
It's statistically significant. It is not practically
It doesn't
significant.
really matter. Because it's-
In the real world, the 2 minutes isn't making that big of a difference.
Maybe they messed up and they put the screw on the wrong.
Yeah, it's like it's not gonna make that big of a difference in the end.
Maybe IKEA didn't drill.
Yeah, exactly. That's a little stupid thing.
By like 4 cents.
Well, most of